telling you, people like this stuff. It's cut and dry. It's the details. The devil in the details is important to me. All right. So we are now, as we're heating our hydrate, going to talk a little bit more about the mold concept which we're using for work of home. We'll continue to work from home. And we'll start back up. Christmas, where's my cursor? Cursoring today. You cursored in class. Okay. Sorry. I find that fun. So we left off with Proust. Okay, which concerns me. I'm really concerned about this. Back then you didn't have photography, right? So you had to hire a painter to paint you. So you had to have money to do this, I guess. And so if someone's going to paint me, I guess you have to be in that position a long time. I'm not sure if that's the position. I don't know what that's about. Now maybe he thought that was his best side. I'm thinking he hasn't found it. We haven't found it yet, but I'm not sure why he's looking that way. I feel like going to paint me, it's going to be like this, right? Maybe it's some push-ups. I'm not sure. But in any case, look at the details of this picture. I'm sorry, this has nothing to do with chemistry, but it's interesting to me. The painter, of course, probably wants to put the best foot forward. Like a photographer, it's the picture, right? I guess you can Photoshop it now, right? But I feel like the painter, you can't. They're kind of photoshopping as they're painting. Ooh, yeah, okay, yeah. In any case, look at his hair. It's like, why are there fuzzies there? Did he want to capture the moment that was really, really fuzzy and out of place, but he didn't want to have too much there? You know, like, why? I'm not sure. Any case, and then of course it's matted straight down in front. All right, any case, Joseph Proust, we love him. He gave us a law of definite proportions. Why? Well, he found that when he found the percent by masses of compounds like water and a hydrate, oh my gosh, kind of parallels, he found that they were always constant. You guys are working from the same compound. You should all get the same percent by masses of water today experimentally. Why? Because compounds have the same number of stuff in them. That was the link to atoms or particle theory. Percent compositions work because the mass of the missing piece is always going to be the constant value because there's the same ratio. In our crystal, there's 5 waters per one of these. So we're always going to get the same ratio of water missing to how much we start with because it's made up of the same type of atoms. Okay? And if you have different compounds, you'll have different what? Percent masses missing or different composition. Okay, so that's important. It's a big tie-in. All right? Any case, this leads us up to John Dalton. Now, he was a crass guy. He was a guy that was, oh, I'm smarter than you. And look at his portrait. And he's like, they're like, yeah, you're not even smart enough to look at me. Okay? So I'm going to look away because you can't even look into my eyes. I'm not smart. I'm just thinking. My portrait says thinking. But in any case, John Dalton was a very intellectual individual. He was actually an English teacher that got interested in science, weather of all things. And he did his own experiments. In fact, he has one major contribution experimentally to this whole idea that there are some particles of matter, atoms. And so using everyone else's research, Joe Proust, Antoine Lavoisier, Robert Boyle, all the people we just talked about, and others, and his own work, it was very clear to him that in order to do the research on gases to understand weather, there must be these particles that all things are made up of, atoms from the atomos. He brought back in the early 1800s, okay, 2,000 years later, first person to bring back the first modern atomic theory, okay? And that modern atomic theory was based upon all the results of all the previous individuals I talked about, including his work. Now, this isn't exactly correct, but for the most part, we still believe this and it works today. So he was the first person to take all that data, think about it, through his own research and other people's research, say that, listen, there is an atomic theory. There are atoms. Clearly the data is suggesting that there are atoms, even though we can't see them yet. And hopefully today we can. He had 5 points. All elements are made of tiny particles called atoms. All atoms of a given element are identical. He said masses. That's not really true. Isotopes have different masses. But he knew that the atoms had to be the same of some type. He didn't know about protons yet. Now we know that all atoms are the same because of the proton number. We'll get to that. The atoms of a given element are different from those of any other element. He didn't know exactly why. He said they were just masses. Of course, we now know it's the proton number. Atoms of one element combine with atoms of other elements to form compounds. A given compound always has the same relative number of types of atoms, law of definite proportions, that coincides with always the same percent by masses of things. Thank you, Proust. Atoms can't be created nor divided into smaller particles nor destroyed. That's not really true. The atoms smash in particle accelerators, so there is some nuclear reactions that don't follow that, but for the most part, what he's talking about is atoms are just rearranging. Okay, and chemical reaction, just separating atoms and rearranging them. And hey, that comes from Antoine Lavoisier, conservation of mass. The mass of the what? Reactants equals the mass of the products, okay, combined. Now, what was his major contribution? Okay, his major contribution was the law of multiple proportions. Now, it's hard to understand because we're looking at chemical formulas. There was no chemical formulas yet. He knew he had carbon. That could be wood burning, okay? And he knew he had oxygen in the air, and he could have purified that. And when he burned carbon with oxygen, he collected a gas. He didn't know it was CO or CO2. This wasn't here. We don't know any of this. But he knew he collected two different gases because they had different densities. And then when he analyzed them from their chemical reactions, in this case it would be an adding mass reaction, but in any case, he found there was a ratio of mass. There was a 3 to 4 ratio of carbon mass to oxygen mass in this kind of gas he collected. Didn't know it was CO. We now know it's carbon monoxide. And then the other chemical made from the same reactants that had a different set of properties that he was able to what? Pull away and purify, had a 3 to 8 ratio of mass. Whoa! Same reactants, elements, made two different products, two different properties, but they only differed from a 3 to 4 ratio to a 3 to 8. This had twice the mass of oxygen than this particle had. And he did this for many other reactions, law of multiple portions. And this showed there was a whole number difference in the mass of oxygen. It was never 0.3, 0.5, 1.7. He said that when you have two different elements making multiple compounds that were different, he knew they were different because they had different properties, density, he didn't know the formula. When he did the math in the reaction to see what the ratio of the mass of the one element to the other, he saw that the one element had a whole number difference. There's twice the mass of oxygen in this gas than this gas. And when we did this in other reactions, it was always a whole number difference. My friends, in chemistry, whole number differences gives credence to whole numbers of atoms. Why is there twice the mass of oxygen in this compound? Because there's twice the number of oxygen atoms. That's the leap that John Dalton made, and he was right. And that's his major contribution to the theory. Okay? And it's done, he did this a whole different elements. Okay, but John had some problems. And the problems are self-made, self-created. He did all of this wonderful work, took all the research, made the modern atomic theory. He gave chemistry a chance, because right now in 1800s, chemistry didn't exist, early 1800s. Nobody could do any calculations. Nobody knew the chemical formulas. No one could predict how much of something I would make if I mixed together. Nobody could. Chemistry, if you can't do math and predict with it, it was just mixing chemicals. Here's his mistake that really hurt chemistry, okay? He proved really atoms existed with all his work, but then he overstepped. Not only did he want to do that, because he's a smart guy and you're not, he wanted to create a symbol for elements. He wanted to create chemical compounds. So he started with an arrangement of what he thought people would write for the atoms. For me, I don't think it was very creative. He might have been smart. For oxygen, he had a circle. For hydrogen, he says circle with a dot in it. For nitrogen, do a circle and cut it in half. He's running out of options, isn't he? Carbon, circle, I'll color it in. This one, we'll just cross it, and this would say peace, and then after that, you just put the elements in. So, I don't know, could be the Easter egg, I don't know, I'm not sure, but this never caught on, okay? But he said, this is how we're gonna do this. Nobody said, and people, again, weren't big fans of John Dalton, the person, but his work was tremendous in establishing atomic theory. The problem is, he even overstepped beyond this. He started putting atoms together. Notice, oxygen is a circle, hydrogen is a circle with a dot. He started putting molecules together. And he said, hey, these are the chemical formulas of these particles. Notice we have the circle, that's the hydrogen, and that's the oxygen, or either one. That's the hydrogen, that's the oxygen. He thought water was a hoe. Okay, he said things that are binary, two different elements, hey, they have a 1-to-1 ratio. Well, we know water doesn't exist that way. And he said that's just the way it is. He had no research to back it up. And so he started writing these chemical formulas of how these atoms existed, and they weren't right, and nobody could do the math to support it. And because he wasn't a nice guy to begin with, and people didn't like his attitude, I'm smarter than you, his overstepping in this area led people to think, well, not only is this wrong, but I think your atomic theory is wrong too. And that kept the idea of atoms down for another almost 60 years, okay? During the same time, there was actually more evidence to support John Dalton. There was a guy named Gay-Lussac, another Joseph Gay-Lussac, Joseph Priestley, Joseph Proust, Joseph Gay-Lussac, okay? Joseph Smith, that's my neighbor. He didn't do anything though. But in any case, this guy was reacting purified gases. And when he did so, this is something that supported Dalton, but Dalton said, because I can't explain it, it can't be right. But in any case, what Gay-Lussac did is he did reactions of gases. He took hydrogen gas, reacted with oxygen to make water vapor. And he found I needed exactly 2 liters of hydrogen, or twice the volume of hydrogen to oxygen, to make 2 liters of water vapor. He saw that there was, again, whole number differences in volume. Whole number. That really supported. Whole number differences mean whole number differences of atoms. But John Dalton said, and a lot of times in Gay-Lussac's work, how can 3 liters of gas react to make 2? They were combining somehow. And John Dalton said, your research is whack. Okay, maybe he didn't use that as words. Okay, he said, you're either missing a volume here, or you're counting one of these wrong. It can't work. Yet, when everybody redid Gay-Lussac's reactions, they find, no, it takes twice as much hydrogen to react with the oxygen to make the same amount of water vapor you start with hydrogen. They got these whole number volume differences, and they somehow combined. Well, John Dalton attacked him, he attacked him, you're not right. Chemistry went nowhere. John Dalton passed away, and here we are in 1859. Chemistry doesn't exist. We don't know what the chemical formulas are. People don't believe there's atoms, even though the research is showing whole number differences. Nobody can do any work in chemistry. Oh, that thing. Cool. All right. Now, we had a conference to fix all of that. 1859. Okay? So Gay-Lussac thought this was all wrong. He said that it was fudged. There was a conference in 1859 to fix all of that. Now, right around the time of Dalton's work, a little unknown Italian physicist, Count Amedeo Avogadro, okay, found that there was really a proportionate piece to all of this. His name is Lorenzo Romano Amedeo Carlo Avogadro di Quararella. Okay, I don't know. I guess he was kind of cheesy. But the point is, he found a link. And here's what he found. It's very simple. He found that when you deal with gases, the volume, the space a gas takes up, is proportionate to how many particles. He called these particles molecules. The word mole is about particles. Now, what's really cool is that his description of molecules was unique. He said, yes, atoms existed as particles. A particle could be a single atom, like argon doesn't bond with anything, so it hangs out by itself. Or a particle could be 2 or more atoms bonded together. This acted as a single particle. That was really important. We all know you take a balloon and you blow into it, it gets bigger. Why? You're adding more gas particles. So gases are flying around, they push off each other. Gases need space. So the more of these particles, the greater the volume. Big deal. Well, if you keep the volumes the same, you have the same number of particles. Whether the particle is bonded to other things or by itself, the particles are the same. Okay, how does that help? Well, in 1859, in an important conference, okay, where chemistry was just not working. It just wasn't doing anything. You couldn't do anything. It wasn't even considered a science. People said, let's go into physics, gosh darn it. You can't do anything with chemistry. A guy named Stanislasio Cannizzaro brought Amedeo Avogadro's work, he was long passed away, into the conference, and he did this, supposedly, okay? He said, take water. Take the work of Gay-Lussac, which we all know is to be true. And Gay-Lussac found that there was 2 volumes of hydrogen, we'll call it H, plus 1/2 the volume of oxygen. And when it reacted to make water, we got 2 volumes. We call this water, because we don't know what the formulas are. And here's what he did. Because of Amedeo Avogadro, these boxes are all the same. We know if we have equal volumes and temperature and pressure are constant, the same number of particles, whether it's a single atom or an atom bonded together, would occupy the same volume, which means they have the same number of particles. So since these are all 1 liter, he said, let's pretend that only 1 particle takes up this space. So let's write an H and draw a circle. And there's an equal volume here, so the equal number of particles. I know that it takes more than just 1 atom of hydrogen to fill a liter, but if volumes are proportionate to how much particles, keep the volumes constant, the particle number should be the same. Hydrogen, it's a bigger particle. And now put them together. Kind of hard. They're going to bond together. And 3 atoms could never make 2 different particles, right? Maybe you'd make this, but we know water isn't made of hydrogen and oxygen separate. We know they bonds together. So the only way to make this explainable, and using Amedeo Avogadro's hypothesis, is hydrogen acts as a single particle because it bonds to each other. And so does oxygen. And if you do this, take 2 H's and 1 O, you've got 1 new particle of water. And the same, another particle of water. Didn't destroy atoms, you just did what? Rearrange them. 1 particle, 1 liter, 1 particle, 1 liter, 1 particle, 1 liter, 1 particle, 1 liter. Same volume, same temperature, pressure, same number of particles. And when you see what you have here, you have what? 2 H2 plus 1 O2 gives you 2 of these particles. You have, for the first time, a chemical formula that's balanced, and you can figure out how much water it was reacting before you can even finish. People were running out of the conference to go to their labs to figure out chemical formulas. And that's where chemistry started. And they all rushed to make chemical formulas, just like you did last night. Your homework last night was building chemical formulas from data, and exactly what they did. What's really, really cool about this is that we were able to see what the atoms look like by using colorless gases. By comparing colorless gases, the same temperature, pressure, and seeing how many, of course, you needed to react. That was Gay-Lussac's work. And using Amedeo Avogadro's, same volume, same number of particles, we were able to build the chemical formulas, okay, and start doing chemistry. Now, if you had the mass of this and the mass of this, you can figure out the mass of your products and start doing stoichiometry, as we'll be continuing to do. This started chemistry, and everyone started building chemical formulas. How did they start? They did a percent by mass procedure. They took the what? Percentage, and they converted the percentage into moles, used the mole formula, and did that way. And we'll talk more, but that's as far as I want to go today. All right? Which is pretty amazing right there. I find it amazing that we're able to see what atoms look like using colorless gases, comparing colorless gases. Crazy. Okay, so we're done with that. Now, what we need